Hi, I'm Dr. Incognito. In this video, we're going to calculate limits at infinity analytically. Our primary focus is going to be on the limit as x goes to infinity of a rational function. That is a polynomial divided by a polynomial. The simplest example of this would be the limit as x goes to infinity of 1 over x. As x grows without bound, its reciprocal shrinks to 0. So this limit is 0. And in order to help us to analyze these general problems, we want to look at a slight generalization of this. Instead of just putting 1 in the numerator, if we have any constant in the numerator, and instead of just x in the denominator, if we have any power of x, any positive power, so n is a positive number, then this limit will also be 0. The denominator is growing without bound. The numerator is a constant, so the fraction will be very small as x grows. So it will shrink to 0. So these limits play an important role in the technique for finding general limits of rational functions. As an example, let's look at the limit as x goes to infinity of 3x squared minus 2x plus 4 divided by 5x squared plus x minus 6. As x goes to infinity, each of these quadratic polynomials will go to positive infinity since the coefficients of x squared are positive. So we have the form positive infinity over positive infinity, which is an example of an indeterminate form. It's an indeterminate form. To figure out what this form represents in this case, the method is to, what I'm going to do is look at the highest power of x in the denominator, and I'm going to factor it out of both the numerator and the denominator. So the highest power of x in the denominator is 2. I'm going to factor x squared from the denominator. And that sounds maybe a little bit strange at first, since you don't have x squareds here or here. But what's going to happen is you're going to leave fractions behind. So when you factor x squared from the denominator, you'll be left with 5. That makes 5x squared. And then plus, you're going to have here 1 over x. When you multiply x squared times 1 over x, you will get x. And then minus 6 over x squared. When you multiply x squared times negative 6 over x squared, you will get negative 6. So you factor x squared from each of the 3 terms, and in situations where you don't have an x squared, you'll be left with a fraction. And that's very important because we understand how fractions are going to behave as x goes to infinity. Okay, so we factored x squared from the 3 terms in the denominator. We do the same in the numerator. Factor x squared from the 3 terms. That way the x squareds will cancel. So you factor x squared and you get 3 minus 2 over x plus 4 over x squared. So whenever you're doing a factorization like this, it's always a good idea to double check it by multiplying. X squared times 3 is 3x squared. X squared times negative 2 over x is going to give us negative 2x. And x squared times 4 over x squared is going to give us 4. So we can check it pretty quickly. Now the point is that having factored the same thing for the numerator and denominator, we can cancel. And the expression that's left, we can deal with term by term. We have in the numerator the limit as x goes to infinity of 3 minus 2 over x plus 4 over x squared. And in the denominator, we're going to have the limit as x goes to infinity of 5 plus 1 over x minus 6 over x squared. And both of those limits can be calculated without too much trouble. What happens to the numerator as x goes to infinity? 3 is a constant, so it remains 3. And then each of these fractions is going to go to 0. So in the numerator we have 3 minus 0 plus 0. And in the denominator we have 5 plus 0 minus 0. So the answer is 3/5. And if we look back at the problem and we look at the answer, this problem is a ratio of quadratic polynomials. As x grows, the significant term is really just a quadratic term. So because x is going to infinity, all that really matters here is the quadratic term, and 3x squared divided by 5x squared is basically just 3/5. So as x goes to infinity, these quadratic polynomials will go to the ratio of their lead coefficients. This is the ratio of the lead coefficients. The lead coefficient is the coefficient of the highest power. So this works out when those powers are the same. You have a quadratic polynomial divided by a quadratic polynomial. The limit as x goes to infinity is going to be the ratio of the lead coefficients. So that leads us to making a couple of other examples. What happens if we make the power on the bottom bigger than the power on the top, and vice versa? So let me change this example slightly, and instead of 5x squared on the bottom, let me make it 5x cubed. And let's see how that changes things. Well, it's still infinity over infinity, indeterminate form. And in this case, the power on the bottom, it's a cubic, it's bigger than the power on the top. Because 3 is bigger than 2. And the rule of thumb is the bigger the power, the faster the polynomial grows. So the cubic polynomial is going to grow faster than the quadratic polynomial. This is basically going to be behaving like a 3x squared divided by a 5x cubed. And then this ratio simplifies to 3 over 5x, which is going to go to 0 as x goes to infinity. The bottom is going to grow faster. The bottom here is growing faster than the top. When you simplify it, the top is a constant and the bottom is growing still. So that limit's going to be 0. So we anticipate this being 0. And to verify that, let's use the method that we just described in the last example. Let's factor x cubed from every term in the problem, from the numerator and the denominator. So x cubed times 5 plus 1 over x squared minus 6 over x cubed. And in the numerator, factor x cubed. Then you have 3 over x minus 2 over x squared plus 4 over x cubed. And then x cubed over x cubed cancels. And now if you look at the limit, as x goes to infinity, in the numerator you have 0 minus 0 plus 0. 0 minus 0 plus 0. And on the bottom you have 5 plus 0 minus 0. So this boils down to 0 over 5, which is 0. So when the power on the bottom is bigger than the power on the top, the answer will be 0 as a general rule. And then if you flip this upside down, the answer is going to be infinity. Well, actually either infinity or minus infinity. So you just have to figure out whether the fraction is positive or negative. And looking at the lead coefficients will tell you that. Okay, so if P and Q have the same power, then the limit at infinity is going to be the ratio of the lead coefficients. If the power on the bottom is bigger, then the limit at infinity will be 0. And if the power on the top is bigger, the limit at infinity will either be plus infinity or minus infinity. And before we leave this topic, let's examine one more example that's not quite a rational function, but it's related. Let's take a look at the as x goes to infinity of the square root of 2x squared plus 1 divided by x minus 3. So we have a square root here, making matters a little bit more complicated. But basically we could guess the behavior by looking at the highest powers. If you ignore the plus 1 here and focus on the square root of 2x squared, then the square root of 2x squared is basically the square root of 2 times x. And then on the bottom we have 1x, and so we get this ratio is the square root of 2. So I'm going to guess that this limit is the square root of 2. But let's be a little bit more careful in computing the limit and see if that is correct. Again, the intuition is that we should follow the highest powers of x. Because if we're letting x become gigantic, adding the plus 1 to 2x squared, or even if we added plus 10x, even if we added plus 10x to 2x squared, if x is gigantic, the 2x squared is going to dwarf the 10x, and it will only be the 2x squared that really matters. Even if x is as small as 100, then this would be on the order, this would be 20,000, and then this would be 1,000. So it would be 20,000 versus 1,000, which is a pretty big discrepancy, and that discrepancy is only going to widen as x grows. If x is 1,000,000, then this one is 20 trillion, and this one is 10 million, and that gap is astronomical. So let's see. The official method is to, we're going to factor out, we can go back to the original problem, this was just a 1. We're going to factor the x from the bottom, and on the top we're also going to factor out an x, but we're going to do so by factoring an x squared out from under this, from the quantity under the square root. So x squared times 2 plus 1 over x squared is under the square root. And then in the next step, I'm going to take the square root of x squared. The square root of x squared, I'm writing x, but I don't want to say it, because it's not always just x. Let's take a look at that over here for a second. The square root of x squared is interesting. Commonly people just automatically write x there, but a better thing to write is absolute value of x. That's correct. If you have something like the square root of -4 squared, for example, that would be 4, which would be the absolute value of -4. So technically the square root of x squared is the absolute value of x, because this is the positive square root symbol. Now, I didn't write absolute value of x here because x is going to infinity. That certainly means that x is going to be a positive quantity, and if a quantity is positive, then the absolute value of the quantity is just itself. If x were going to negative infinity, that would change things. If x were going to negative infinity, then if x were negative, the absolute value of x would equal, what would that equal? That would equal negative x. If x were negative, then negative x would be positive. Okay, but in our problem here, x was going to positive infinity, so the square root of x squared is x. So again, we cancel the x's like in the last examples, and when we take this limit, the fractions go to 0, and so you can see we have the square root of 2 plus 0 divided by 1 minus 0, and that's the square root of 2. Okay, so there's a look at limits as x goes to infinity of, we discussed rational functions in great detail, and here's an example of a slightly more complicated example involving a square root as well. Okay, thank you for watching.